Becky, are you ready?
Yeah, sure.
Okay, let's start.
Okay.
Good morning, good afternoon, and good evening. This is Paul from NC State, and welcome you to the World River and the Delta System Source to Think webinar series. Today is our great honor to invite Professor Becky Dorsey from University of Oregon come here talk about tectonic controls on sediment discharge and delta erosion, particularly in the earlier Pliocene of Colorado River. So before I introduce Becky, as always, I would like to mention this since August 2020, 2 years ago, and we started this webinar series together with, during the pandemic. So far, we already have 131 talks archived on our YouTube channel. So you can access these resources through this tinyurl.com/S2S talks. So it's a great resources for teaching and research. And at the same time, we also maintain this Twitter account, Source to Think. As you can see, we will post the weekly the talks, new publication, conference information. So if you are using Twitter, you're welcome to follow us. And next week, we back to the original time, East Coast of 9 a.m. We will have even Dorsey come from Dartmouth College, come here talk about rapid changes to global river suspended sediment flux by humans. Please see our email or Twitter announcement. And Professor Rebecca Dorsey, we see Becky, as mentioned, Professor, University of Oregon. And so she graduated from University of Vermont, and then master degree of Princeton University, PhD degree, Princeton University, then assistant professor in Northern Arizona and the University of Oregon, and then department head 2013 and 16, and then professor until now. Her research mainly focused on field-based study of the late Cenozoic sedimentary basins across the range of tectonic setting, with the overarching goal to understand the environmental, structural, and the tectonic controls on sedimentation. And her current research including, the lower Colorado River area, the basin development in the active arc-continental collision of Taiwan, and the geonomics study of the Earth's life erosion in the Baja California. And so, Becky, now I give the floor to you. Now you can share your screen and start your talk.
Okay, well, yeah, thanks so much. And it's really a pleasure to be here. I will go ahead and share and get things set up here. Let's see. Pull out that pointer. Okay, great. Well, thank you so much, Paul, for organizing this wonderful seminar series. And thanks to people who have shown up today. It's really an incredible series on source to sink processes that you have put together here, and it's really an honor to participate. So I want to start with that thanks, and also to acknowledge so many collaborators, students, many students and colleagues who have contributed to our understanding of the development of the Salton Trough and the Gulf of California region and the lower Colorado River. Couldn't do it with all of the contributions of a great team of colleagues, and also acknowledge support from the National Science Foundation. So as Paul said, I want to talk today about the emergence and early evolution of the lower Colorado River. And I'm going to highlight the influence of the San Andreas Fault here, as you can see along the plate boundary, and particularly the Eastern California shear zone. And what I'll try to show you is evidence that during the early stages of development of the Colorado River here, sediment of the river became trapped as a result of subsidence and fault-bounded basins. And this resulted in large fluctuations in river sediment discharge, which in turn produced a surprisingly large-scale regional back and forth migration of the Colorado River Delta. So that's the main story. And the outline here is today I'll start with some key concepts in sediment routing systems. I'll introduce you to the Gulf of California and Salton Trough transform margin here. We'll take a quick trip through the stratigraphic record of the early Pliocene Colorado River and its delta system, and that will provide the evidence for the story that I've summarized here. And so the takeaway message here is to really highlight the important role of structurally controlled sediment routing as a factor that can influence the evolution of large river deltas in tectonically active settings here and elsewhere. So we'll illustrate that with the example here. So starting with a few concepts of source to sink and sediment routing that I'm sure we're all quite familiar with. The figure on the left is by Phil Allen that just shows the basic elements of erosion in a source area, sediment transfer through that river routing system, and then accumulation and deposition in a basinal sink. And many important studies you can see cited here, Kessel, Stort, and Van den Driesche and Phil Allen are important landmarks in understanding how that works. Now, on the upper right is a map from Michael et al. 2014, who worked out a sediment budget for Eocene sediments in thrust-bounded thrust-top basins in the southern Pyrenees. And what they showed here with this sediment budget approach is you can see in this model, which resulted from a lot of data collection, that the sediment emerges from an eroding source, as shown here, and it enters the river channel network with a sediment discharge or flux indicated with the arrows. And as the sediment moves along, it also is getting deposited as represented by the red boxes, and deposition is actually acting to extract or remove the sediment discharge from that river load. And this effect becomes especially exaggerated if a basin is bounded by faults. Then the faults are likely to cause more rapid subsidence, which in turn results in trapping sediment, and it just accentuates that effect of extracting and removing the sediment from the load, and that results in a decrease of sediment discharge in the downstream direction. Now, this can be understood in terms of quantitative sediment mass balance and sediment continuity, which has been established over decades of modeling and field-based research by Chris Paola, again, Phil Allen and others. And this diagram is one way to kind of summarize that effect. And what we can see is the idea is that if we have a condition of equilibrium where there's no change in elevation over time, then if we have a relatively closed system for our sediment, it's not escaping out to some other route, because sediment is typically funneled in a downstream direction. And so what that means is that the predicted downstream decrease in sediment discharge from upstream to downstream is going to be directly proportional to the rate of subsidence as indicated here. And that can be predicted with a lot of confidence and a lot of success will be the fate of that sediment. So again, we see here the trapping of sediment as a result of tectonic subsidence that creates a decrease in sediment discharge downriver. And this can have an important effect. We can expect this to have an important effect on large rivers in tectonically active settings. Indeed, a number of people have looked at this kind of effect around the world. And in this figure from Liu et al. 2009, we see the very large rivers of Eastern and Southern Asia discharging sediment out to the Yellow Sea, South China Sea, and elsewhere, representing like 70% of the sediment flux to the world's oceans. And what they said in this paper, this is our own Paul Diu who's hosting this series, and what they noted was that in these rivers, about 1/3 to 1/2 of river-derived sediments are trapped in the river's low reaches and contribute to extensive floodplain and delta plain development. So this is a really important aspect of large rivers, small rivers, medium-sized rivers. And you can see the very large historical sediment discharge rates here for these major rivers. Now, despite those very large sediment discharge rates, we also understand that large modern deltas are mostly being drowned by the compounding effects of rising sea level and the reduction of sediment flux to the deltas. And this is, again, because of the trapping of sediment in reservoirs behind dams. And in this provocative figure by Gio-san et al., 2014, they show, they plotted the sediment available to deltas, that is being delivered by river discharge, compared to the sediment which is needed to maintain each delta in the event of a 1 meter sea level rise in the next 100 years. And they showed that virtually all or most of the world's large deltas fall below this stability threshold, which means that there's not enough sediment to maintain the delta, and that the deltas are already starting to be submerged and retreating. Now, it turns out that sediment trapping is also important at geological timescales, and we can study the stratigraphic record to find out and understand more about how fault-driven subsidence along a river network might control the evolution of ancient deltas in tectonically active regions. And so that brings us to the Colorado River in the southwestern US. It is the 4th largest river in the conterminous United States, with a catchment area of 630,000 square kilometers. It's a major source of water for the southwestern US. And as we all realize, this region is really struggling with the current mega drought. The Colorado River, prior to the installation of dams, had a very large sediment discharge of 150 to 200 megatons per year. And that historical pre-dam value is surprisingly similar to the extended geological sediment flux rate that has been calculated for the past 5 million years. Now, after the dams were put in, this resulted in a huge decrease of the sediment discharge, down to like a reduction by like 3 orders of magnitude to very small sediment discharge, currently reaching the north end of the Gulf of California. So the Colorado River traverses out of the Colorado Plateau, down some lowland river valleys, and right across the Eastern California shear zone, which is part of the Pacific North America plate boundary fault system. And it enters the Salton Trough here at Yuma. And the river sometimes flows into the Gulf of California, as we expect, and then sometimes it flows into the Salton Trough to create episodic lakes, including the Salton Sea today. And so what we're looking at here is a dextral or a right lateral transform margin that was initiated about 25 million years ago, and it has continued to grow and evolve since that time. The modern configuration of the plate boundary includes the San Andreas Fault in the north here. It goes through the Big Bend, which is a large restraining bend, and then it enters the Salton Trough, which is a pull-apart basin, a releasing bend pull-apart basin. And adjacent to that, we have the Eastern California shear zone, which is a network of trans-tensional strike slip, linked strike slip, normal and oblique slip faults, which are part of the overall plate boundary strain that accommodates the relative motion between the Pacific plate and the North American plate. And finally, all those faults then are linked down to the southeast into the Gulf of California, which is our a very highly oblique transform margin with long transforms connected by short spreading centers. Now we'll take a slightly closer look at the Gulf of California. And so here's a map from an earlier paper. And again, we can see then the relative motion of the Pacific plate and the North American plate in the dextral transform motion. And the Baja California microplate is moving obliquely away from mainland Mexico as a result of offset on these long transform faults, which are connected by short seafloor spreading centers or oceanic rifts. And the northern part of the Gulf of California is basically a large composite pull-apart or step-over basin here. Now, what we can also see is the bathymetry is much deeper in the south, and it gets progressively shallower and shallower toward the north or northwest here. And we can characterize these subbasins as sediment-starved to filled in the shallow basin in the north, and then it's actually overfilled, resulting in terrestrial conditions here in the Salton Trough. And this bathymetry and the distribution of water depths is entirely the consequence of voluminous input of sediment from the Colorado River over the past roughly 5 million years. So We, as geologists and stratigraphers, we want to understand the early Pliocene development and birth and early development of the river. And so to do that, we'll shift our attention a little farther north. And so this map shows the lower Colorado River as it goes through the various faulted terrains of the Eastern California shear zone here to Yuma. Here's the San Andreas Fault in a bit more detail and its associated faults, San Jacinto, Elsinore, and so forth, and the Cerro Prieto Fault connecting down to the northern Gulf of California. Now, in order to study the geologic history of this region, we need to look at the stratigraphic record. And to do that, we'll be looking at the 5 to 6 million year old Bouse Formation, which formed in a chain of lakes in the north, and then a shallow marine sea in the south. And so this pale white area shows the area of latest Miocene inundation represented by the Bouse Formation. And then the yellow splotches are the areas of outcrop exposure. And our work has focused in the southernmost exposures of the Bouse Formation in the Cibola area. And we can correlate and compare the record of the Bouse Formation with a similar age stratigraphic sequence exposed in the Fish Creek-Vallecito Basin over here in the Western Salton Trough. Now, because the Vallecito Basin is moving with the Pacific Plate, then if we want to look at where those sediments were located, about 5 million years ago, we have to undo that dextral motion and restore that basin back to the south, and that places the Fish Creek-Vallecito Basin here south of Yuma about 5 million years ago. So what I'm going to do is first take a trip through the stratigraphy of the Fish Creek-Vallecito Basin, and then we'll look at the Southern Bouse Formation, and we'll talk about the sequence of events and the controls on those events. And this is a geologic map of the Fish Creek-Vallecito Basin, modified from earlier work by Charlie Winker, Gary Axon, and John Fletcher. And what we see here is kind of a complicated geology, but it's not too bad. This black line here is has been mapped out as the regional low angle normal fault, or West Salton Detachment Fault. And all of the red in the western part of the map area is crystalline, Cretaceous crystalline rocks that sit in the lower plate or the footwall of that normal fault. And then all the other colors are in the hanging wall. And these blocks were sliding down during deposition, during slip on the West Salton Detachment Fault, which also resulted in accumulation of sediment in this area. Now, the pink color here represents upper plate basement rocks, and then all the other colors are sedimentary rocks of the Split Mountain group and the Imperial group, shown here in blue, and then the Palm Spring group. And this whole area is a 15 to almost 20 kilometer wide panel of uniformly southwest dipping sedimentary rocks. So the oldest rocks are here in the northeast, and they get progressively younger and younger toward the southwest. And the total section is about 5.5 kilometers thick, as measured at the surface. And a few units that I'm highlighting here are the Wind Caves member sandstone, which is this yellow patch. It's fairly restricted to a small area. And then it is directly overlain by the Coyote clay, which is this blue strip that I'm showing here. And that is, well, I'll tell you more about the Coyote clay. The important thing to note here is that the Coyote clay is regionally extensive and is much more extensive and widespread and goes way out into the basin compared to the aerially restricted Wind Caves member. So again, a southwest dipping stratigraphic section. So we'll look at the lower half of that in this column here. This is a figure from our 2011 paper, and what we did is we measured a lot of section, and we used paleomagnetic data and uranium lead tough ages higher in the section to work out the ages of the deposits. We also really relied on and applied the results from earlier studies by Charlie Winker and Sue Kidwell, who worked out like this entire succession and all the depositional environments of the basin, the Fish Creek-Vallecito Basin. So you can see the section starts with alluvial fan conglomerate resting on crystalline basement rocks, and there's an abrupt marine flooding surface right here directly on top of a large sturstrom, and that we have the first marine turbidites of the Latrania Formation. And then after another sturstrom, we see the base of the Wind Caves member, which is again on the map illustrated right here. And our our age data indicate that the base of the Wind Caves member, which is also the earliest Colorado River sand in this region, is about 5.3 million years old. Now, a recent study by Crow et al. Suggested from detrital sanidine dating that maybe these oldest river sands are about 500,000 years younger and perhaps as young as 4.8 million years old. And we think that that's unlikely, but it also isn't really important for the story that I'm telling you today, because any change in the absolute age would not change the relative chronology that we have really nicely laid out here and the sequence of events that I'll be describing. So the Wind Caves member is gradationally overlain by the Coyote clay, which is that distal marine clay stone. And then, as you can see here, there's like 1,000 meters of section that consists of shallow marine deltaic sandstones, marine rhythmites, and a gradual transition to the fluvial sands and muds of the Arroyo Diablo Formation. And this was all worked out by Winker and Kidwell. And then more recently, a new study by Ray et al. Has confirmed that interpretation and refined it because they recognize that actually this succession represents what they call a compound cliniform delta sequence, which I can't get into the details, but they did a beautiful job of identifying the offshore subaqueous cliniform and tidal dominated shelf subaqueous platform deposits with a shoreline cliniform and the transition right into the fluvial deposits. So that's a really exciting new development. So what I'm going to do is to just show you a few examples of these deposits and talk a little bit more about how we can use them. And the first is the Wind Caves member, which is a really interesting unit of thick-bedded, sand-rich, channelized turbidites that accumulated in a submarine canyon at the base of a paleo slope. And we can see that these are clearly derived from the Colorado River based on distinctive petrographic features. And we can also use the measured thickness and distribution of the Wind Caves member to estimate its volume. And we know the time over which it was deposited, which means that allows us to calculate a paleo sediment discharge, or paleo QS, which winds up being about 6 to 20 megatons per year, which is typical for a lot of average global rivers, but is much less than the long-term average for the Colorado River, which we worked out in a prior study that I did with Greg Lazier. So we'll hang on to this idea that this is a relatively low paleo discharge compared to the long-term average. Now, the Coyote clay gradationally overlies the Wind Caves member. Here you can see it in the field, the transition from the upper Wind Caves into the Coyote clay. This is an ultra fine-grained sand-starved marine clay that records the rather complete shutdown of sand output from the Colorado River right at about 5 million years ago. And you can see it's overlain here by the marine rhythmites of the Mud Hills member and then the base of the Yuha member, which is actually the subaqueous rollover documented by Ray et al. But this shutdown of sand is really important for understanding the river evolution, and is similar to other examples of sediment shutdown documented in submarine fans from places like thrust top basins in Italy, offshore borderland basins in California, submarine fans in the Karoo Basin, and as generally applied to understanding sequence stratigraphy. So I'm going to skip right over this 1,000 meters of deltaic sediments. You'll have to read the paper by Ray et al. to check that out. And here we finally get to the beautiful fluvial cross-bedded sandstones and overbank finds that accumulated in large channels of the Paleo Colorado River as the river finally arrived as a culmination of that prograding delta. And here's our paleogeographic reconstruction, which shows that the river sediments just filled the Paleo Valley at this time. And it's important to note that the Colorado River Delta prograded into the basin during an abrupt increase in subsidence rate, and the fluvial conditions persisted over large area during rapid subsidence. So this requires a large increase in sediment flux, which is consistent with our calculations from that prior study that recognized this large sediment flux since in the past 5 million years. And this behavior of prograding delta, despite other adverse conditions, is seen in other supply-driven delta systems. So with that, then we'll shift our attention upstream and look at the correlative record in the lower Colorado River Valley here. And again, we can correlate then the section at Fish Creek-Vallecito Basin to the southern Blythe Basin. And that's going to be the southern Bouse Formation, which we've spent some time studying over the last 5 to 10 years. And so this is our summary stratigraphy for the Bouse Formation. And it's important to keep track that the Bouse has 3 members. The basal carbonate member is a mixed siliciclastic bioclastic unit that formed in a tidal strait setting. And it actually deepens up from tidal to subtidal. And then the second member, the siliciclastic member, consists of Colorado River sediment that shows a distinctive coarsening up pattern that records the progradation and arrival of the river and the delta. And the third is the upper bioclastic member, which is especially important because it formed in a marine bay that requires a marine reflooding of that lower river valley after the river first ran through it. So I'll go through these 3 members, starting with the basal carbonate member. And this is our paleogeographic reconstruction based on a lot of detailed stratigraphy and facies analysis in these areas of Bouse Formation exposures shown here. So we see that the basal carbonate member accumulated in a fault-bounded tidal strait with this interesting dog leg sort of bend, which results from the curious fault geometries of the Paleo Eastern California shear zone. And in this cross section, you can see the basal carbonate member is this very thin unit at the bottom, which is overlain by thicker siliciclastic member deposits. Most of these sediments are still concealed beneath the modern floodplain, but they're quite well exposed around the edges of the basin. And this whole gentle sort of tapered geometry represents a sag basin that subsided gradually during faulting. Now, the basal carbonate is just full of tidal deposits and marine fossils. We have lots of distinctive tidal features, including dune crossbedding and coarse grainstone, abundant wavy flazer and lenticular bedding. We've documented sigmoidal crossbedding with spring neap tidal bundles and reactivation surfaces, and there's lots more. Brennan O'Connell and Kevin Gardner did some beautiful work on the Bouse Formation, and we got this all worked out pretty well. And that's all I'm going to tell you about the basal carbonate member. It is overlain. You can see in this summary diagram, the basal carbonate is overlain by the siliciclastic member, which begins with green claystone directly overlying the marl of the basal carbonate. And it passes up section into red mudstone and siltstone with abundant desiccation cracks and root traces and weak paleosols. And it in turn is overlain by a large cross-bedded, multi-story trough cross-bedded sandstone, which records deposition in a fluvial channel system, and therefore it represents the first arrival of the Colorado River at about that time. And again in the Bouse Formation, we see this systematic coarsening up section, which is readily interpreted in terms of a prograding delta. And here we borrow the model from Petruno and Helen Hansen, and to just sort of recap then that the green claystone is, we can interpret that as a pro-delta deposit, and it as a result of delta progradation, we have the arrival of delta front and channel mouth bars represented by the mudstone and siltstone facies, and then finally the Colorado River itself arrives as recorded in these multi-story cross-bedded sandstone deposits. So this is the record of the first arrival of the Colorado River in the lower river valley about 5.3 million years ago. And the age of this deposit is based primarily on 4M biostratigraphy that Chris McDougall has done a lot of work on, as well as correlation to the Fish Creek-Vallecito Basin. Now we need to talk about the upper bioclastic member. So this unit is especially important because we see that it formed in a shallow marine bay as a result of marine reflooding of the lower Colorado River Valley after the river first ran through it. And we see water lane, ripple bed forms in sandy bioclastic carbonate, various hummocky types of wave-formed deposits. We also have documented some interesting cross-bedding that resembles hummocky cross-stratification in rather poorly sorted conglomerate, which we finally concluded probably was deposited by tsunamis in a tectonically active setting and a restricted marine bay. Now, the marine origin of the upper bioclastic member is confirmed with the presence of this distinctive coralline-like calcareous red algae. Is the most distinctive fossil in this unit, as well as other marine fossils, including echinoid spines, barnacles, clams, marine foraminifers, and serpulid worms. So let's see, to recap then, the basal carbonate member formed in a fault-bounded tidal strait. The siliciclastic member preserves that coarsening up section that records the delta progradation and the first through flowing Colorado River, but then it's overlain by this enigmatic marine unit that records marine reflooding of the lower Colorado River Valley. And that's the curious thing here. So we can look at that evolution through time and put that into space using this map here from our geosphere paper. And this is important work based on the reconstruction that Scott Bennett and Mike Darren and Mike Oskin and Paul Umhofer and many of us have been working on over the years. And it shows the Paleo Eastern California shear zone was a very active set of linked strike slip, dextral, normal, and oblique slip faults that were active in the lower Colorado region during the time of deposition of the Bouse Formation. So we start with the deposition of the basal carbonate member in this fault-bounded tidal strait. And then shortly thereafter, we have evidence of the first arriving Colorado River. And notice the Creek-Vallecito Basin down here that we talked about earlier in its reconstructed position relative to Yuma. And during that time, then there was this initial flux of sediment produced turbidity currents that moved down a submarine canyon and deposited these channelized sand-rich turbidites that we call the Wind Caves member at the base of that slope. Now, that all is happening around 5.3 million years ago, according to our chronology, but it's the next thing that's surprising, and that is the large-scale retreat and transgression of the delta back up the lower Colorado River Valley, maybe more than 100 kilometers, as documented by the upper bioclastic member here in this area, as well as the deposition of the Coyote clay in the more distal setting in the Fish Creek-Vallecito Basin. So this represents a retreating, a transgressing bayhead delta that formed during that shutdown of sediment discharge from the Colorado River. And so we want to know what caused that shutdown and the nearly complete turning off of river sediment discharge at about 5 million years ago. And this is another map from our geosphere paper that highlights that the Eastern California shear zone is a broad belt of faults, but only the western part of it is active today, with these yellow lines indicating modern fault ruptures, ground ruptures. And the green eastern part represents what we call the Paleo Eastern California shear zone, the part that was active 5 million years ago and is not very active today. So can we tie these things together? And I think that we can. So we are proposing that the shutdown of sediment discharge at 5 million years ago was related to an episode of strike slip and normal faulting in the Death Valley area, as well as the greater Eastern California shear zone. So because so many people study the Death Valley area, we have a good chronology, and there's a lot of evidence that at about 5 to 6 million years ago, this area lit up with tectonic activity, as documented by the development of the fault zone, faults in the Furnace Creek fault zone, thermochronology in the Black Mountains, and the syntectonic deposits of the Copper Canyon Formation. So what's important to note is that the faulting did not just happen in the Death Valley area. That's just where it's been better dated. And what, in fact, those faults were linked to the regional faults of the rest of the Eastern California shear zone, including these basins along the lower Colorado River. And that faulting episode we proposed had two major effects. And one was to create a rise in relative sea level right along this basinal corridor as a result of tectonic subsidence, and that's nicely recorded in the basal transgressive ravinement surface at the base of the Bouse Formation, the upper bioclastic member here. And we think that that also produced a decrease in the river sediment discharge as a result of increased subsidence rates and sediment trapping, as discussed previously. So what we can do is to pursue that just a little farther, is to see if we can actually find sinks where that sediment might have been stored. So we're gonna zoom into this area and look at some potential sediment sinks. And here's that map. It's a rather simplified map that just shows a few of the major basins: Cottonwood, Mojave, Chemehuevi, and Parker basins along the lower reaches of the Colorado River. And so this yellow area represents the sediment that was arriving into this lower part of the river at about 5 million years ago. And we start by asking, well, what was the volume of sediment produced by the upper Colorado River arriving here at this yellow arrow at about 5 million years ago? And we can use the paleo sediment discharge that we calculated previously from the Wind Caves member, and the duration of that shutdown of sediment discharge, which is bracketed between 100 and 300,000 years, 0.1 to 0.3 million years. And that gives us an estimated total sediment volume produced of 375 to 3,000 cubic kilometers. So that's the amount of sediment we need to store someplace in order to effectively shut down what gets out of the Parker Basin down here in the south. So then what we can do is, I've just done a simple estimate to kind of bracket or ballpark the volume of sediment that's potentially stored in these lower Colorado River basins by using existing geologic maps and some subsurface information. For example, in the Mojave Basin is like a 3 kilometer deep basin, and although the age of those sediments is not known, we can certainly imagine that a good portion of that sediment may have accumulated right here during this period of interest. So I've estimated, you can look at the area of the basins and then just work with minimum and maximum values for the average thickness and calculate the volume. And these volumes over these periods of time represent accumulation rates in these basins of roughly 0.2 to 6.7 or 7 or 8 millimeters per year. So these are all reasonable accumulation rates for that period of time. And what we find then is that the sediment that's potentially stored in these basins is overlaps completely, almost completely, with the volume that was produced by the upper Colorado River during that 100 to 300,000 years. So they're very similar values. And what that means is that the sediment trapping hypothesis is supported by a simple estimate of the mass balance analysis. So hasn't been fully tested because we haven't dated the sediment in these subsurface basins, but it certainly appears to be a plausible explanation. So finally, then what I'll do is review then the controls on the transgression and regression of this regional delta system between about 6.5 and 4.5 million years ago by converting our stratigraphic sections from thickness to time and comparing the record in the lower Colorado River Valley to the record in the Salton Trough. And we can compare them to the record of global sea level rise and fall from this recent update by Miller et al. 2020. And what I've done here is I've labeled the major events in terms of transgression, regression, transgression, and regression. And we can start by interpreting the shoreline shift that is associated with the regional transgression that deposited the bioclastic facies of the basal carbonate member, as well as marine turbidites in the Salton Trough. And that transgression can be attributed to a regional tectonic subsidence that occurred along the entire plate boundary from the southern Gulf of California, right on through Santa Rosalia, past the middle to central to northern Gulf of California, right on up into the Salton Trough. So the entire plate boundary was opening up at that time. And clearly the transgression at that time is related to tectonic subsidence. And but then we have this major advance in the first establishment of the Colorado River as it came down through the lower Colorado River Valley and was deposited as the oldest marine turbidites in the Wind Caves member. And that's a major regression that reflects an initial sediment flux that probably, although I haven't really discussed those conditions, it probably is related to a climate change which was occurring in the latest Miocene into the early Pliocene, that is increasing rainfall that led to the filling up of lakes on the Colorado Plateau and the lake spillover off of the plateau, as documented by Kyle House and his colleagues, that show there's a series of top-down filling and spilling events that initiated that early Colorado River. The less expected next step here is another regional transgression that re-flooded the lower Colorado River Valley. And as you just saw a few moments ago, we interpret that to have resulted from some combination of tectonic subsidence along the lower river corridor, as well as a major decrease in the sediment flux, which may be largely attributed to trapping of sediment along the lower Colorado River basins. And finally, a major increase in sediment flux results in the return regression, deposition of the Bullhead alluvium, and this major deltaic progradational coarsening upward section that results in the arrival of the river in the Salton Trough at about 4.5 to 4.2 million years ago. Now, the reasons for that large increase in sediment flux are not really well known. It could be related to adjustments on the plateau, perhaps the Green River was being captured at that time, as well as possibly the end or a slowing down of that tectonic subsidence, which had defeated the delta during this time. So those are some definitely open questions. Now, what we can also say is that changes in global sea level were not a major factor in these regional transgressive and regressive episodes, because there's little or no change in sea level through this time. And in one example here, starting around 4.8 million years ago, we actually see a rise in global sea level during the time of this major river regression or progradation. What we do see is evidence for a major pulse of extension and subsidence at about 5 million years ago in Death Valley and the greater Eastern California shear zone, which we propose trapped sediment along the river basins for a period of time and resulted in this temporary but pronounced decrease in river sediment discharge. So I'm going to wrap it up here with just a few concluding comments. We have shown evidence for highly unsteady punctuated sediment discharge during the early stages of the Colorado River, and this was actually unexpected and has led to a lot of thinking about how river systems behave within an active fault zone. And it turns out, just to conclude, that we think that trapping of sediment in these basins here, north of Parker and including the Parker area, resulted in more than 100 kilometers retreat of the delta during a temporary shutdown of river sediment discharge, and that was due to sediment trapping in those river subbasins. This was followed by a large increase in sediment discharge to the modern pre-dam rates that have been roughly 150 to 200 megatons per year over the last 5 million years. So we think that this represents an important process that helps us understand the evolution of continental scale rivers and deltas here, and may likely also apply to other tectonically active settings. And what's curious to note is that the large shutdown of sediment discharge and the drowning of that delta is comparable and similar in many respects to the dramatic effects produced by trapping of sediment by modern dams and reservoirs in many large modern rivers. So it's interesting to compare those to each other, the volumes, the rates, the sediment mass balance at different timescales, and the similarities of those two sets of processes. So I'll stop there and happy to chat or answer questions. Thanks.
Becky, this is a great talk. So now, the audience now is able to unmute yourself, and you can ask Becky the question directly. Hey, Michael, yeah.
Hi, Becky.
Hi, Mike. Good to see you.
Hi. Yeah, good to see you. Really nice putting together. I'm going to ask, because at times I've heard of the Colorado River discharging further south in the Gulf of California, and I don't know if that's before then, or if it's a possibility of happening here?
I think that's an idea that's been floated around, but I don't think that it ever gained really any traction because you can't really trace it, and there's not very good evidence for that. I think what we could say is, looking at this map actually, that during around this time, early Pliocene, latest Miocene to early Pliocene, these faults were active. And so we have a suggestion that the crust was being dropped down in this area along this corridor. So although I can't rule it out completely, and maybe the shutdown could have resulted from a big switch and then redistributing the sediment discharge farther south, I suppose, is a possibility. I couldn't rule it out, but I in the Yuma area, there's it's my understanding that the subsurface data in the let me go back to that last slide, in the Yuma area reveal a fair amount of sediment in this area in the subsurface, but there's never been detected out here farther to the east, which would be required to funnel it farther south into the Gulf of California. But if you know of something that I'm forgetting, I'd love to hear about it.
I don't know of any direct things, and in fact, it would be hard to move it because you have to go across the Gila River drainage. To do that.
Exactly. Yeah.
Hey. Anybody else? Yeah, other question. So Becky, what the area you studied is a great. Now we can see the delta, the claniform, on land. And what could we learn this for us to understand the modern delta? If we try to understand the claniform or subaqueous delta system. I mean, can we apply that, what you observed, the sequence stratigraphy for us to understand the modern system? Or?
Well, that's a really good question. I mean, I'm still kind of absorbing these new results by Ray et al. This is a really important paper. I think it's the Journal of Sedimentary Research. And the recognition of the compound claniform delta system is, I think, still in its relatively early stages of development and sort of processing what it all means. And I don't think I'm really the person to lead that discussion, but Cornell, Olario, and Ron Steele and others at UT Austin are really on it. And I think that what it potentially means is you might have opportunities for, say, more pathways for bypassing of sediment. If you get, but the sediment that's going to be bypassed beyond the shallow shelf platform is mostly going to be mud. I mean, that's what they see in their facies models, and that's what you keep seeing in the stratigraphic record. Is that you might have on a steep shelf. Sorry, a narrow shelf with a steep slope, then your sand can bypass down to the base of that slope. But once you build a larger shelf platform, then your sand is likely to get reworked and stay on the shelf. And what they see in the models and what they're finding from their stratigraphic examples is that the outer shelf rollover, the subaqueous rollover, and then the transition down to that more distal shelf is mostly mud. Those are mud facies. And actually the rhythmites of the Mud Hills member, and then underlying that, the Coyote clay itself actually fit into that whole model pretty well. So those are pretty fine-grained mud-rich sediments. But I don't know how that might translate into thinking about sediment budgets, on sort of different timescales. It's a really good question. I'm not sure.
Yeah, sometimes we're working on the modern system, and because we cannot directly observe, and we have to rely on sub-bottom profiler or polling. Sometimes we are, in a dilemma, but working on this system, sometimes really open our eyes.
I will say that Ray et al. The other thing that Ray et al. Did is they didn't only interpret the stratigraphic record as a compound cliniform delta, but they also were able to identify it in the modern Colorado River system. So
Okay.
yeah, so that you can look at they looked at bathymetry and distribution of sediment and bed forms and so forth to identify the compound cliniform in the modern Colorado River Delta as well. And so you can see how they did that and maybe apply that to other settings. Yeah.
That's good. Okay, wonderful. So Scott from USGS.
Hey, good morning, Becky. Great talk.
Hi,
Great.
Scott.
I think you've laid out a really great case of kind of the interaction and evolution of a river delta along an active plate boundary. Have you seen, or have others seen direct evidence of earthquake activity in the sedimentary record? For example, seismites or liquefaction features or other kind of tectonically related phenomena that you would see in the stratigraphic record?
Yeah, actually, there are a few places in the siliciclastic member of the Bouse Formation in the southeastern Palo Verde Mountains. There's some spectacular large-scale sediment mass liquefaction structures. They're pretty surprising large-scale features. And we never did very much with that, but it they're surprisingly large scale blobs of sediment that just went up. And we think that these are big liquefaction features and that they're most likely produced by seismic activity. And then also in the, so then the basal carbonate member up in the Trigo Mountains has a whole slump fold complex that probably requires some shaking because the depositional slopes were so gentle at that time. You needed something to get that to take off down a very gentle slope, probably also evidence of seismic shaking. So those are two examples from the Bouse Formation. And then I think, in the, down in the Creek-Vallecito Basin, I mean, the whole thing is tectonically active during that time. And probably many of for example, the Sturstrom deposits, those large scale rock avalanche deposits are most likely triggered by large earthquakes.
Sure.
Yeah, for sure.
Great. Thanks, Becky.
Okay, any other question? So anyway, Becky's talk is also will be available on the YouTube. So if you know any other question or comments, and thank you, Becky, again.
Yeah, thank you
For this wonderful talk. I think many people will able to watch the recorded version.
Absolutely.
And maybe send you an email if you have any question. Okay, cool. So maybe we can stop here. Thank you. See you
Great.
next week. Yeah.
Thanks so much. Thanks again.